Tonight we're going to talk about polyprotic acids. So poly meaning many, protic referring to a proton. So polyprotic acids have two or more ionizable hydrogens. And these will be ionized in successive steps. So an example is, I think my pen isn't out working. Oh dear. So we have an example here. This is sulfurous acid, H2SO3. So H2,
So many technology troubles today.
not a good night for technology. Okay, so in general chemistry, acids are always written with the ionizable hydrogens first. So H2SO3, both of these hydrogens can be ionized. So the first one comes off, leaving us with the hydrogen sulfite ion, and that has an acid ionization constant. And then that ion also has an ionizable hydrogen, and that can come off, leaving us with the sulfite ion, and that has its own Ka. That second Ka is going to be a lot smaller than the first Ka, and one of the reasons for this is here we have a hydrogen ion leaving a neutral molecule, whereas in the second step we have a hydrogen ion, a positive ion, leaving an anion. And so there's much more attraction for the hydrogen ion, and so it's harder to leave, and therefore Ka2 is smaller. Here are common polyprotic acids and ionization constants. So here we've got oxalic acid, sulfurous acid, phosphoric acid, citric acid, ascorbic acid, carbonic acid, and then way up here at the top is sulfuric acid, and sulfuric acid is special because it is a strong acid in the ionization of its first proton. So this only has one Ka, Ka2, because the first hydrogen ion comes off completely. Yes?
So the different Kas are related to the different protons that come off?
Yes, Ka1 is the first proton coming off. Ka2 is the second one. If there's a Ka3, that's the third one coming off. And so we see as you go from 1 to 2 to 3, those always become smaller. How do we find the pH of a polyprotic acid solution? Well, that first Ka is a lot larger than the second or third. So the amount of hydrogen ion formed by that first step is larger. In addition, the formation of hydronium ion in the first step inhibits formation of hydronium ion in the second step. So most of the time, we can treat polyprotic acids as if the first step was the only one that was important. Major exception is a dilute solution of sulfuric acid, where we've got that first one that comes off completely, but the second one will also play a part. So let's find the pH of a 0.05 molar carbonic acid solution, and we're given Ka1 and Ka2. So we'll look at the first ionization and then the second ionization. So H2CO3 will be in equilibrium with H plus and bicarbonate ion. And then the bicarbonate ion is also acidic and can lose a hydrogen ion, leaving us with the carbonate ion. Bless you. So we're doing ice tables here. So this is the initial concentration of carbonic acid, so 0.05. And what do we put for the initial concentration of hydrogen ion? Approximately 0. And then the hydrogen carbonate ion will be 0. And then we're going to look at how these change. Well, all the coefficients are 1, and so we're not going to have minus 2x or anything. It's all x's. So the reactant is going to lose x, and the products will gain x. And then at the end, we've got 0.05 minus x, and we've got x and x. So Ka1 is the hydrogen ion concentration times hydrogen carbonate ion concentration divided by the carbonic acid concentration. So we have x times x divided by the quantity 0.050 minus x, and they tell us that that is equal to 4.3 times 10 to the minus 7. So we can try using the x is small approximation to see what we get. So we're saying x is small enough that subtracting it from 0.05 doesn't really change anything. And so then we'd end up with x being equal to 0.050 times 4.3 times 10 to the minus 7, and the square root of that. So that's what my calculator is giving me. I'm going to take that and divide by 0.05, multiply by 100 to check that the approximation is correct. And I'm getting that as being 0.3% of 0.05. And so we can use that approximation. You can also, of course, use the solver in your calculator and do the whole thing. Okay, so we found x. How is x useful to us? We're trying to find the pH, right? Pardon me?
Take the negative log of it.
Yeah, so we could look at this and just take the negative log of this, which is the hydrogen ion concentration, to get the pH. But there's also this second reaction that's happening, right? So this one happens first, and then we can look at the equilibrium and the ice table for the second one. So maybe this one will be green. So we found that x was equal to this. So what is the initial concentration of HCO3 minus now? It's not 0 anymore, right? After this first equilibrium occurs, now the initial concentration for the next one is x, which is 0.000. I'm just going to call that 1.5 because there's not much space here. Does that make sense? What's the initial concentration of hydrogen ion? It's not 0 anymore, is it? Because from this first ionization, we've got 0.00015 molar hydrogen ion. What can we say about the initial concentration of carbonate ion? That's going to be 0. So do you see how that first ionization inhibits the second ionization? Because now we have all this hydrogen ion from the first ionization, and that's a product in the second one, and so that's going to cause this equilibrium to lie further than to the left than if that first ionization had not occurred. So we've got our final concentrations or our equilibrium concentrations from the first ionization, and we use those for the initial concentrations of the second ionization. So again, this one is 0, and so the only possible direction that this can go is forward, because 0, we can't have less than 0. So this is minus x, and this is plus x, and that's plus x. And so we're going to have 0.00015 minus x, 0.00015 plus x, and x. So our equilibrium expression is very similar here. It's the products times each other divided by the reactant. So Ka2 is going to be the hydrogen ion concentration, 0.00015 plus x times x divided by 0.00015 minus x. If we apply the x is small approximation, saying that these numbers are small enough that they are not going to affect this number when subtracted or added, then we end up with x being equal to Ka2. So that made things really simple. So we found x, and we're trying to find the pH. So we want to look at the hydrogen ion concentration here at equilibrium. And it would be 0.00015 plus x, but we just determined that adding x doesn't do anything to that number. So the hydrogen ion concentration is equal to 0.00015 molar, which is what we got after the first one, right? The second ionization didn't affect the pH at all because it was so small. So the pH, I'm going to go back to that 1466 number. And negative, whoops, I don't know what that was. Oh, I see what I'm doing. Yeah, I'm pushing the wrong buttons and I'm getting this differential thing, and I'm like, wait a minute. So pH is 3.83. 2 sig figs here because of the 2 sig figs in the equilibrium constants. Any questions? So did we have to do the second ice table? No, we didn't. So that's what we're saying, that usually, almost always, the second ionization does not contribute significantly to the pH, and so we don't need to worry about it. 3.83. The one exception, though, was a dilute sulfuric acid solution. So here, we're asked to find the pH and the sulfide ion concentration of a 0.0075 molar sulfuric acid solution. They're only giving us Ka2. Why is that? Because it's strong in its first ionization. Sulfuric acid is on the list of strong acids, but only the first proton is strong. So what we've got here is we've got H2SO4 is going to ionize completely to form hydrogen ion and hydrogen sulfate ion. Whoops, not a 2, just a 1. So that's going to happen completely. So if we started with 0.0075 molar sulfuric acid, and essentially none of that, and none of that, then all of this is going to go away. And so our equilibrium concentrations for the hydrogen ion and the hydrogen sulfate ion after the first ionization, those will be equal to 0.0075 molar. But then we need to look at what happens when the second hydrogen ionizes. So this is not a strong acid. These will be our initial concentrations. So 0.0075. Where that came from. Let's see, this is I, 0.0075, and the sulfate will be 0. So we are finishing chapter 17 tonight, and we've been doing a lot of ice tables, right? We are not done with ice tables at the end of chapter 17. We're going to be using them all through chapter 18. So if you have any questions about how these things work, now would be a great time to ask questions. So there's initial, and we've got change and equilibrium. So we're going to lose X from the reactant. We're going to gain X for each of the products. 0.0075 minus X, 0.0075 plus X, and X over there. So Ka2 we're going to get something that looks a bit like what we had on the previous example. So my equilibrium concentration of hydrogen ion is the initial plus X. For the sulfate, I've got 0 plus X. And for the hydrogen sulfate, I have 0.0075 minus X. And that is equal to our equilibrium constant here, which is 0.12 times 10 to the minus 2. Is that kind of big or kind of small for equilibrium constants? That's kind of big, huh? That's 0.0012. A lot of what we've been seeing are like minus 5, right, or even smaller. So we can see if the X is small approximation is going to work. So that means that this would be 0, and that would be 0, and then we'd have that situation where X is equal to the equilibrium constant, which in decimal form would be 0.012. Is that small compared to 0.0075? No, it's actually significantly larger, right? So we can't do that here. We can't do X is small. So bust out the number solver. So 0.0075, or you could work this all out into a quadratic. Yuck. made a mistake in my equation, so then I get a ridiculous answer. Okay, and there I'm getting a negative answer, so that's not good. So I'm gonna change what I'm starting at, because I did not start at 0. There we go. X is equal to 0.00385. Anybody else get that number?
Yeah.
Good. Either we're all right or we're all wrong together. Yes?
Well, in the final exam, the ACS thing, will it be like
There will be no solving quadratic equation problems on the final. Yeah, they don't do that. Mhm.
What about a chapter test?
On the chapter tests, I don't think there are either. Yes?
How did you get the concentration for the H plus and the HSO4 ion? in the
That's a
first
great
test?
question. So I got these concentrations because I know that that first hydrogen ion ionizes completely.
Oh.
So this goes to completion, right? So then I have none of this left, and all of it becomes this and this. So that's where those numbers came from. Great question. Any other questions? So we found X, but we want pH, right? Oh, I'm making a mess. Change color so it doesn't get all lost. So our hydrogen ion concentration is going to be 0.0075 plus X. Plus 0.003854. 0.01135. Good grief. So 1.94. So I'm putting 2 decimal places because 2 significant figures is a reasonable number of sig figs in this problem because of the equilibrium constants. And then the other question is, what's the sulfate ion concentration? Well, the sulfate ion concentration is just X. So the sulfate ion concentration, that's not sulfate. This is going to be 0.003. If we're going with 2 sig figs, that would round up to a 9. Any questions? Any questions?
I'm not getting the same X, but I'm
Okay, let's look at it. So let's see if we got the right answers. That used 3 sig figs, not sure why, but it's close enough. Okay, so the second ionization is not going to affect the pH for most diprotic acids. But sometimes we need to know what the concentrations of the anions are. And in order to do that, we do have to consider that second ionization. So how does this work? So here's our first ionization. Here's our second ionization. If we want to find HX, we're just going to calculate hydronium ion concentration for weak monoprotic acid. That's just one ice table. That's basically the same process as finding the pH. But if we want to find that second ion it's missing both of its hydrogen ions, then we're going to have to do what we've done in the past couple of examples just to see what happens, and use the initial concentrations from that first ionization as the initial concentrations, I mean the equilibrium concentrations, as the initial for the second ionization step. Basically, we're going to do it again. So this is asking us to find the carbonate ion concentration of the 0.05 molar carbonic acid solution in for practice 1717, which we already did. Okay, so there I was able to retrieve our scribblings, well, my scribblings. So here what we did is we looked at the first ionization and we found that X was 0.0015 essentially, and we plugged that in over here for a second ice table, right? So when we get here, we find that the X is 0 approximation is valid, right? And when we do the math here, we end up with X is equal to the ionization constant. Yeah, that's what it is, a constant. So is 5.6 times 10 to the minus 11 0? No. It's really small. It's really close to 0, but it's not actually 0. So if we want to know the carbonate ion concentration, what's that going to be equal to? This X that we found. This is small enough that it did not affect the hydrogen ion concentration, it did not affect the pH. But there is a little bit additional hydrogen ion, and that is equivalent to the additional carbonate ion. Any questions? I'm just going to leave it here because I would just be doing the same thing on the other slide. Yeah.
Is it usually going to be equal to the constant then?
Yes, it will often be equal to the second equilibrium constant, Ka2. Yep. Of course, there's all kinds of other things that can happen. You can have things where there's some other source of one of these ions, and so that makes everything more interesting. Yeah.
Can you move back, please? Oh, okay. So, for the initial oh, never mind. I was reading.
Okay.
That is different.
Yeah.
Okay, thank you.
Yeah, so to find the answer to that other slide, I think it was for practice 17.19, if you hadn't already done this part, you'd have to do that part. And then you'd go over here and do this part, and you can use the X is small approximation, and you find out that X is a very small number. X is equal to that carbonate ion concentration that we were looking for. Yeah, and there's the answer. So let's look at the dissociation of a polyprotic acid. So here we have, honestly, I can't remember the name of that, but that's okay. A polyprotic acid. And so we lose one hydrogen and we have the anion here. And then we lose the second one, and then we have the 2- anion here. And so we're getting hydrogen ion from the second one. And to find the total, we're going to be adding those together, right? The second concentration of hydrogen ion is insignificant relative to the first. So we end up with that concentration being equal to Ka2. When the X is small approximation is valid, which it usually is.